Hi, I'm Arif Masrur, a PhD candidate at the Department of Geography. Here I am presenting one segment of my dissertation research. The topic of my presentation is interpretable spatiotemporal random forest for predictive modeling in wildfire ecology. Machine learning methods are increasingly applied to large heterogeneous geospatial datasets for predictions and explanations of geographic events for their high predictive power, generalizability, and robustness. However, an apparently high predictive power may oftentimes lead to unreliable results when ignoring spatial dependency, temporal non-stationary data patterns during model building and validation process. Also, many machine learning models are often criticized for their intricate inner mechanism that prohibits to understand how machine learning makes its predictions. Machine learning interpretability is a rapidly growing area of research. Previous non-geospatial studies addressed machine learning interpretability issues from global and local interpretability perspectives. Global interpretability focuses on explanations at the dataset level, whereas local interpretability focuses on individual prediction level. We are looking into feature prediction relationships and decision paths of those predictions. Here we focused on the interpretability of random forest as it is perhaps the most widely used model in wildfire ecology due to its superior predictive performance. Although it is intrinsically interpretable compared to deep learning algorithms, its general inner mechanism is not decomposed to the spatial and temporal dimensions because it uses total randomness in generating its submodels known as decision trees and uses bootstrap aggregation of all decision trees predictions to reach a final prediction for a test data sample. This essentially introduces its prediction reliability as well as interpretability issues in geographic application contexts. Therefore, in this research, we have proposed an evaluated and interpretable and spatiotemporally explicit random forest modeling framework for predicting and analyzing wildfire occurrences in the United States. More specifically, first, we have adapted and extended the general random forest algorithm for spatiotemporally explicit model training and predictions based on spatial and temporal calibrations in the model building process. Second, in the modeling framework, we have introduced interpretability workflow to explain prediction decisions in geographic contexts. Third, we have implemented and demonstrated this framework using large-scale wildfire ecology case study of the United States. For the case study here, we used historical wildfire dataset available through the monitoring trends in burn severity program and temporally aggregated environmental data from the TerraClimate dataset. We also used North American Ecological Regions Level 2 vector dataset for spatial sampling of annual wildfire and environmental driver data across 25 ecoregions in the United States. These ecoregions represent holistically distinctive components of ecosystems. Thus, ecoregions can serve as an ideal spatial framework for sampling spatial data in machine learning modeling that would enable assessing spatially variable relationships and relative importance of factors influencing wildfire across the United States. For predicting or classifying wildfire occurrences in the United States, in our proposed approach, first we merge dependent and independent variable data sets. Then we systematically sample training data in space and time based on spatial dependence and temporal non-stationarity criteria. After that, we train decision trees for each of the sample subsets of the original training data. For prediction on a test sample, as opposed to the bootstrap aggregation used in general approach, here we use spatial and temporal constraints and weights-based approach, which I introduce in the next slide. In the final step, we focus on model interpretation at the regional and individual sample levels using decision path similarity, for example, and also for focusing on understanding feature similarity among local models. In the individual level, we focus on feature prediction relationships and understanding important features and thresholds. In our experimental modeling design, we use different spatial as well as temporal constraints and weights to examine how the characteristic spatial dependence and temporal patterns in data manifest in the predictive performance. Also how they provide different insights into the wildfire ecology of the United States. These constraints and weights are used for selecting relevant local model or decision trees, and they are predictions for test samples. We introduce spatial dependence by considering only nearby regions decision trees for prediction. We introduce spatial heterogeneity by considering both nearby and distant regions decision trees for predictions. Similarly, we examine temporal nearness and distances of temporally sampled decision trees in relation to the candidate test samples predictions. Here you can see model diagnostics of our 9 experimental models. Experiment 2 that introduced both the spatial dependence and heterogeneity in the model performed best among all spatial constraints and weight-based models. It took majority vote from test data samples own region and combination 2 regions decision trees. Some are distant and some are nearby. Among temporal criteria-based models, experiment 9 performed superior to others, potentially due to incorporating enough variability in the predictor space by taking majority vote among temporally neighboring decision trees that are 5-year preceding and following the test fire sample, for example. We compared prediction performance of our sampling-based approach with regional models based on general random forest. For that, for each region, we have used 1984 to 2016 data as train samples and 2017 data as test samples. This introduced class imbalance issue. That's why on the left side of this table, we report model accuracy comparison with imbalanced data. And on the right-hand side, we compare models with balanced data, that is after under sampling the majority class. In most cases, from these two comparisons, as you can see, our approach performed either equally or better compared to general random forest approach. Here we show spatial distribution of prediction accuracy from our spatially sampled models. As just highlighted in the last slide, almost all regions in experiment 2 have a high predictive accuracy that is greater than 80%. After investigating predictive power of our proposed approach, we looked into its interpretability, which has been a major focus of this research. We asked both local and global level interpretation questions. Local interpretations focused on individual sample level, whereas global interpretations focused on regionally aggregated level explanations of prediction decisions. By doing so, in fact, we can answer interesting questions from fire ecology context. Due to the time limitation of this presentation here, we quickly highlight on this interesting local interpretation question. We wanted to see how the relative importance of different environmental factors for a sample's prediction are distributed across space. Each of these points represent a regional decision tree and its prediction for a test sample. You can see that on the graph and also on the map. Based on our proposed approach, we can see how two decision trees that are similar in feature importance on the graph are actually located over geographic space, which provides insights into spatial similarity of environmental feature importance for a prediction. Next, we looked into what worded rules environmental variables formed for a prediction. By comparing these two local decision trees, we can see very high summer temperature in one decision tree mostly contributed to its correct prediction. Here we look into regional level interpretations. As you can see, as opposed to the general spatial random forest, we can reliably get insights on the similarity and differences in environmental variable importance across regions. And here our approach allows reliable understanding of temporal change in environmental variable importance. Finally, we looked into exploring the relationship between an important environmental variable's partial dependence on the likelihood of wildfire occurrence. These graphs from our approach can give you insights on the regional patterns of relationships and threshold values of environmental factors for wildfire likelihood. The key contributions of this research are: we introduce spatiotemporally explicit model training and predictions for predicting geographic phenomena using random forest with a desirable or acceptable predictive accuracy. Our interpretable spatiotemporal random forest approach enables spatiotemporally meaningful or reliable prediction of geographic phenomena. It can be used as exploratory modeling tool that can offer interesting insight into models' prediction decisions in spatial and temporal contexts. For example, spatial heterogeneity in feature prediction relationships, temporal patterns, or change in relationships and spatial thresholds. This approach can be applied to other spatiotemporal data-based application contexts in geosciences, spatial business intelligence, and spatial epidemiology. With that, now I would like to answer any questions you may have. Thank you.